Alright gang, here we go. This is for Chem 2 Unit 9. We're talking about chemical kinetics today. We're specifically talking about relative rates using stoichiometry as well as determining rate laws using known concentrations. Alright, so last video we talked about using being able to determine what the rate of change of reactants and products would be, and we specifically focused on one-to-one relationships, and then now we're just going to briefly talk about what is it like if it's not one-to-one. This isn't too bad here. So if you have ozone converting to oxygen, we know that for every 2 ozones we produce 3 oxygens, and so therefore, or O2s, and so therefore the rate of our reaction would be equal to -1/2 times the concentration of ozone, and that would also be equal to the positive 1/3 concentration of oxygen. Alright, so essentially all we have to do is just take these coefficients, throw them out front over the inversed, right? And then if it's a reactant, it's still negative, it's a product, it's still positive. Okay, so let's do a practice problem here. Let's not do this one. Let's do this guy here. Practice exercise 1. Alright, it says at a certain time in a reaction, substance A is disappearing at a rate of 4 times 10 to the negative second molarity per second. Substance B is appearing at a rate of 2 times 10 to the negative second molarity per second. Substance C is appearing at a rate of 6 times 10 to the negative second blah blah. What of the following could be the stoichiometry for the reaction being studied? Alright, so it says that it says A is disappearing, and then B and C are both appearing. So that means A has to be the only reactant, and B and C would be products. So we can cross out any of these where B is a reactant. Alright, okay, so now we're down to C, B, or D. Alright, B, C, or D. And it says B is appearing at a rate of 2, and that's the lowest one. So that means B and C should be a 1:3 ratio. And then A would be a 2 ratio, so the answer would have to be C. Alright, cool. And then this guy here, what if the rate of decomposition of dinitrogen pentaoxide in the reaction of this at a particular instance is 4.2 times 10 to the minus 7th molarity per second? What is the rate of appearance? Alright, of NO2. So if this guy disappears at 2, or this guy appears at this fast, then for every 2 of these, we get 4 of these. So we divide our 4.2 by 2 and then multiply it by 4, right? And we'd get that nitrogen dioxide. And then for oxygen, we just divide it by 2. So for NO2, the rate would be 4.2 e to the negative 7th divided by 2 times 4, right? Or just multiplied by, oh, I guess I could have done that in my head. Oh well. 8.4 times 10 to the minus 7th molarity per second, and then the oxygen would be that guy divided by 2, and I'm going to do this one in my head. It'd be 2.1 times 10 to the minus 7th molarity per second. Okay. Now, this is where life gets more exciting. All right, so we've got we want to be able to determine the effect of concentration on rate. Okay, so remember a couple videos ago now we talked about the 4 main things that affect our reaction rate. Okay, and one of those things was concentration. Okay, and so we want to, and since concentration is really easy to mess with, it's really easy to just add more or less moles. We want to be able to quantify exactly how does this concentration affect it. Okay, so we're going to come up with this idea called a rate law, and in order to figure out the rate law, we need to figure out how each individual reactant affects the reaction rate. Okay, and so in order to do that, we're going to keep every concentration constant except for one reactant. All right, one reactant, and then to see what happens to the rate. Then we change a different reactant, and we do this until we see how much each reactant affects the rate. Okay, so for example, all right, we're going to do a couple of these here. For this guy here, we've got the reaction of ammonium and nitrite and water. All right. And these are both our reactants, and they're combining to form something. It doesn't really matter what. All right, and we've got run 6 experiments, 1 through 3. These 3 here show how the ammonium affects the rate, and these 3 here show how the nitrite affects the rate. Notice that in 1 through 3, our nitrite is left constant. It's 0.2 each time, and then our ammonium goes up. It's doubled each time here. And then in 4 through 6, the opposite occurs. We have the ammonium held constant, and then our nitrite is doubled for each time. And then on the far right here, we see the rates. Okay, so when reaction 1, the rate was 5.4 e to the negative 7th, etc., etc. All right, so what we're going to do is we're going to look at these guys and we're going to say, okay, so from reaction 1 to reaction 2, what exactly happened? Well, we took our nitrite, remained constant, and our ammonium doubled. Okay, and so what we want to do is be able to establish a ratio. And essentially what we're going to do is we're going to say, well, the rate of whichever reaction we're talking about, specifically we're doing reaction 2, over the rate of reaction 1 is going to be equal to the concentration of ammonium, okay, in reaction 2 over the concentration of ammonium in reaction 1. And we're just setting up a ratio here. Okay. Now, in order to make these truly equal to each other, we'd have to raise this guy to some power. And this x value right here is what we're trying to solve for. Okay. So if we look at this, we can see that our ammonium was doubled. It was from 0.01 to 0.02, and then our rate went from 5.4 to 10.8. So that was also doubled. All right. So so if we plug these in here, okay, this is the exact same thing we had here. So this guy, so the rate 2 over rate 1, well, that'd be equal to 2, and then the ammonium concentration for 2 over 1 would also be 2, and we want to solve for this x value. So the x would have to be 1. Okay, so the order with respect to ammonium for this reaction is 1. All right, so that's important. That 1 is going to play a part when we write out our rate law. Okay, so that 1 is what we're looking for. Now we're going to do the same thing with ammonia, or with the nitrite, excuse me. So with the nitrite, we'll look at 4 and 5 here. So now we're going to establish the same thing. So it would be the rate of reaction 4 over the rate of reaction 5 is equal to 0.0202 over 0.0404, and then this would be raised to some power. Sorry, and I should have written this out as concentration of nitrite in reaction 4 and concentration of nitrite in reaction 5. And it's going to be raised to some power. Okay, and I've completely screwed it up. Here, let me erase this real quick. We'll just take a step back. Take a step back here, because I wrote it upside down. I'm sure a bunch of you guys are screaming at your screens. Well, I guess it really doesn't matter because I did 4 and 5 here. Usually you want to do the higher ones on top just because it makes life easier. Whichever one's going to give you a whole number. Okay, so we'll put reaction 5 here and reaction 4 here. There we go. All right, and then so here we'll put the concentration of nitrite, and then the concentrate in reaction 5, and then the concentration of nitrite in reaction 4, right? And we're solving for this x value. And so we can see that as we solve for 5, or we solve for this guy here, our rates went from 10.8 to 21.6. So this guy's doubled, all right? So it would be 2 is equal to, and this guy here from 0.404 to 0.0202, that would also double, so 2 to the x. So again, our reaction is order 1 with respect to the nitrite, okay? So this gets us to this idea that we can write out the rate law. Okay, the rate law is always going to be, look in this value here, we're always going to have the rate is equal to some k value, and we'll talk in depth what that k value is here in a second, times the concentrations of the reactants to their order, okay, and then concentration of B to its order, x and y. All right, and so, and really we need a variable for each reactant that we have, okay, because each reactant has the possibility of affecting the rate law at different values. All right, so the rate for this particular one, because the ammonium is reactant order 1, and the nitrite is reactant order 1, they're both order 1, okay, and so this would be the rate law for this reaction. And you can see how this would be really helpful. If we know this k value and we know the initial concentrations, then it'd be really easy to figure out how fast the rate is going to be. All right. So a couple other things about rate law that you need to know. The exponents tell the reaction order with respect to each reactant. We understand that. That's why they both had exponents of 1. So this one, you know, we had a 1 here and a 1 here. Okay. The reaction overall is second order. Okay. In order to determine the overall reaction order, we're going to add up all the exponents. Okay. So we add up all the orders for each individual thing to get the overall reaction order. So this K value is the rate constant, all right? And the rate constant is a temperature-dependent variable. Each different reaction has its own rate constant, and that rate constant changes with temperature. And that makes sense because we know reactions change, their speed will change based on temperature. So if we increase the temperature, it should probably also change the rate of the reaction. So that K value keeps track of our temperature portion of our reaction rate, because we know the concentration is not the only thing that controls our reaction rate. Okay. So the other thing, all right, one other thing here is that the order of the reaction must be determined experimentally. Okay, it is not based on stoichiometry. Sometimes it looks like it might match that, but it's not necessarily given. So for example, this guy here, dinitrogen pentoxide decomposing, all right, it's balanced. It would have a 2 in front of it, but the rate law looks like this. Okay, notice that it's just a first order with respect to the dinitrogen pentoxide. All right, but then this guy here matches exactly what you'd expect. The rate law equals concentration of hydrogen times the concentration of iodine. So these coefficients that are out front really mean nothing when we're talking about rates. Okay, it's all based on experimental data. That's really the only way in order to figure out what your reaction rate is. All right. So the K value also gives us an idea of whether or not our reaction is fast or slow. Okay, if our K value is 10 to the 9th or higher, okay, then we consider it a fast reaction. If it's 10 to the 9th or lower, we consider it a slow reaction. Okay, so if you solve for your K value, then we can, and it's, 10 to the 15th, that's a pretty dang fast reaction. Or if it's 10 to the -3rd, that's a pretty dang slow reaction. All right, so let's do one of these practice problems here. It says, consider a reaction A plus B yields C, for which K equals concentration of A times concentration of B squared. Each of the following boxes represents a reaction mixture. A is red spheres and B is purple ones. Rank these mixtures in order of increasing reaction rate. All right, so the rate, okay, of box 1 would be equal to K times the concentration of A. Well, there's 1, 2, 3, 4, 5. All right, so 5 times the concentration of B squared. And I'm just using this equation right here because this allows me to calculate rate. All right, and there's 1, 2, 3, 4, 5. So this would be 5 squared. So 5 times 25 would be 125K. And they don't tell us this K value, nor do we really need to know it in order to rank them based off their rate, right? Okay, so, and then rate 2 would be K, and then, so there's 1, 2, 3, 4, 5, 6, 7. 7 of these guys, and then 1, 2, 3 blue ones, or purple ones. They say they're purple, but they kind of look, I guess they're purpler than this blue. But anyway, so 3 squared, so that'd be 9 times 7, so that's 63K. All right, and then rate of box 3 would be K times, and there's 1, 2, 3 reds, and then 1, 2, 3, 4, 5, 6, 7 blues. So 7 squared, so that'd be 49 times 3. So 50 times 3 would be 150, and then it's, so it'd be what, 157? Is that right? 147. 7 squared times 3. Yeah, 147. That's what I said, 147. Okay, 147K. So the fastest reaction would be 3, and the slowest would be 2. So it'd be 2 is slower than 1, which is slower than 3. So there'd be that's our ranking here. All right. So now we're gonna blow through some of these guys here. All right. All right, so now let's talk about this real quick. What are the overall reaction orders for the reactions described in equation 14.9 and 14.11? And then they also want us to decide the units for these guys. All right, so these reactions are back here. So we're going to go back here real quick. All right, so this is this guy right here. So we got to determine a couple of things. We got to figure out what the reaction order is, and then also what the R values are, or what the units for K are. Okay, so it's pretty easy to figure out what the reaction order is. Okay, because all we do for the order is we just add up the all we do is add up the exponents. So this is a 1, so it'd be order equals 1. All right, so the order for this one, well, it'd be 1. Why is it doing that to me? All right, 1 plus 1, so that's 2. Okay, and this guy's order would be 1.5, but he's an odd duck, so we're going to ignore him. All right, Now we have to figure out the units. Okay, now just to take a step back, we know that the K rate is going to be equal to the K times our concentrations, right? So our rate, the units for our rate, always have to be in molarities per second, right? That's our base unit for K, right? So that means whatever our units for our K value is, whatever this is has to equal these molarities, however many there are, okay, times some value that goes in here. We have to figure out what those molarities are. So let's do one real quick. So let's do this guy here, 14.9. Okay, so if our rate, all right, our rate, molarity per second, is equal to our K value, so this is where our K would go, okay, all right, our units for our K, and then that would be times the concentration of the molarity, okay, so that would be molarity here. Okay, so what would have to go in this box in order to give us these units? Well, the molarity is already on top here, so we don't need anything in the numerator, and then in the denominator we just need a seconds. So the units on the K would be would just be per seconds, 1 over seconds. All right, let's try 14.10. Okay, so the rate, all right, would be equal, so this is the molarity per second, is equal to our K value, all right, times the concentration of H2 times the concentration of I2. All right, so our K value, well, we don't know what that is yet. We got to figure that out. Times the times the molarity times the molarity. All right, so we need to figure out what goes in here in order to give us molarity per second. So we've got one too many molarities here, so that'd be a 1 over molarity times seconds. And you can see if we multiplied this out, one molarity would cancel and we'd be left with just this. So the units for this one here would be K is equal to 1, or the K units would be 1 over molarity per second. All right, so that's an important skill to be able to do. They're kind of tricky.